Welcome to the Creating and Simulating AMD Vitis Model Composer Designs Tech Module. Here is the agenda for this tech module. We will focus on providing an overview of the AMD Vitis Model Composer tool, explaining how to create and simulate HDL, HLS, and AI engine designs, explain how to create a heterogeneous design, that is, a design with both AI engine and programmable logic components, and then summarize. Before we start, let's go over what AMD Vitis Model Composer is. The AMD Vitis Model Composer tool accelerates development by offering a productive environment within MathWorks Simulink for simulation, analysis, code generation, and hardware validation. Vitis Model Composer is a model-based design tool that enables rapid design exploration within the MathWorks MATLAB and Simulink environment, and accelerates the path to production on FPGAs and adaptive SoCs through automatic code generation. This tool provides a library of performance-optimized blocks for design and implementation of algorithms on FPGAs and adaptive SoCs using HDL, HLS, and AI engine blocks. You can focus on expressing algorithms using blocks from these libraries as well as custom user-imported blocks without worrying about implementation specifics and leverage all the capabilities of the Simulink tool's graphical environment for algorithm design, simulation, and verification. Vitis Model Composer transforms your design to production quality implementation through automatic optimizations. Model Composer can be useful in the following three types of design flows. Model Composer is very useful for algorithm exploration, design prototyping, and model analysis. You can use the tool to flesh out an algorithm in order to get a feel for the design problems that are likely to be faced, and perhaps to estimate the performance and resource utilization in hardware. The work is preparatory, and there is little need to translate the design into hardware. You might also plan to use a Model Composer design as part of a larger design. For example, Model Composer is a good setting in which to implement data paths and control, but is less well suited for sophisticated external interfaces that have strict timing requirements. In these cases, it may be useful to implement parts of the design using Model Composer, implement other parts outside, and then combine the parts into a working whole. The third possibility is implementing a complete design. When your Model Composer design is complete, everything needed for a design is available inside Model Composer. For such a design, clicking the Validate button instructs Model Composer to translate the design into respective HDL, HLS, and AI engine source files, and to write the files needed to process the design using downstream tools. If you want to describe Vitis Model Composer in a nutshell, the tool provides a rich library of blocks that allows you to quickly build a design. It allows you to build a heterogeneous design where there is both programmable logic and AI engines, and you can then co-simulate the design to verify the results. It provides code generation capabilities where you can generate HLS code from HLS library blocks, RTL, such as VHDL or Verilog, from HDL blocks, or adaptive data flow graphs from AI engines, allowing you to accelerate your development. On top of everything, it automates moving your design into hardware so that you can easily validate that the design works. Before we delve into the details, we'll start by showing you a typical Model Composer design. Vitis Model Composer is built on top of MathWorks Simulink products. In this design, the input on the far left of the design is created based on Simulink source blocks. This design is a heterogeneous design, so it has both AI engine subsystems as well as PL blocks, and in this case, the PL is in the form of an HLS kernel block. On the very right is the scope part, which allows you to view and analyze the output of the design. Now let's overview the AMD toolbox and library blocks. Simulink provides a library browser where they provide a variety of blocks for different applications. The Vitis Model Composer adds an AMD toolbox to this library. It is a collection of blocks that are highly optimized for targeting both programmable logic and AI engines, as well as a collection of utility blocks. It also enables importing custom HDL, HLS, and AI engine code as blocks into the tool. You can focus on expressing algorithms using blocks from these libraries as well as from custom user-imported blocks without worrying about implementation specifics and leverage all the capabilities of the Simulink tool's graphical environment for algorithm design, simulation, and verification. Let's take a closer look at these libraries. In the AI Engine library, we have a rich collection of AI Engine DSP-related blocks targeting both AIE and AIE ML devices. This makes it much faster for you to put a DSP design together in Vitis Model Composer for AI engines and analyze and explore the design. The AI Engine library also contains blocks to import kernels and graphs that can be targeted to the AI Engine portion of Versal devices. Once your AI Engine design is ready using these blocks, the tool uses an x86 simulator to run simulation for faster verification, which is bit accurate, but not cycle accurate. The tool can also transform your AI Engine design specification into a top-level connected graph to implement AI Engine-based devices. Likewise, the HDL library in Vitis Model Composer offers a collection of the DSP blocks. These DSP blocks are cycle accurate and bit accurate in simulation, and most of them have C models where it makes the simulation much faster in Model Composer than an RTL simulation. Xilinx System Generator, the previous standalone design environment for developing DSP algorithms and generating HDL as an output, is now part of the Vitis Model Composer HDL library. These library blocks leverage the IP core generators to deliver optimized results for the selected devices. The HLS library in Vitis Model Composer offers predefined blocks that include functional blocks for math, linear algebra, logic, and bitwise operations. These blocks also have C models that allow fast simulation in Vitis Model Composer. The tool transforms your algorithmic specifications into production quality C++ HLS code implementation through automatic optimizations. The utility library in Vitis Model Composer contains common utilities such as Vitis Model Composer Hub, connectors used to generate output and analyze blocks that support connections between AI Engine, HDL, and HLS libraries, and other common utilities for building and debugging the application. Now let's look at how to create and simulate an HDL design. Here is the general flow for creating homogeneous designs using HDL, HLS, or AI Engine library blocks. Creating the design and simulating steps are performed using the Simulink software along with the simulators, whereas analyzing, validating on hardware, and exporting the design are performed using the Vitis Model Composer hub block. Let's focus on the first two design steps, creating and simulating an HDL homogeneous design. Let's look at the process that you can use to put your design into hardware via Vitis Model Composer and the Simulink tool. You build a design by dragging and dropping blocks from the library onto a new sheet. You can right-click a block to format. As there are a vast array of blocks already accessible from the libraries in the Simulink software, trying to locate a specific block can sometimes be challenging. You can use the Find feature at the top of the Simulink library browser to search for a block. Once the block is added, you can right-click the block to format it or double-click the block to configure it for different block parameters. Once all the required blocks are added, you can connect the output ports of the block to the input ports of other blocks with signal lines. Signal lines define the flow of data through the model. Vitis Model Composer also provides a separate set of library blocks for handling super sample rates under the HDL library. Super sample rate, or SSR, is a parameter that determines how many parallel samples to accept for every clock cycle. The SSR feature is widely applicable to all our devices, especially for Zynq UltraScale Plus. This feature is beneficial for users who cannot use the hardened RF SoC digital up converters and digital down converters. The use of SSR blocks avoids manual and structural modifications to a design, which accelerates the design cycle. Model Composer currently supports 25 vector blocks that can be accessed from the Simulink library browser. Here's an example of a Vitis Model Composer HDL design. You can see the Simulink software sources, the gateway blocks used to interface between the Simulink software and Vitis Model Composer blocks, Model Composer HDL blocks, and the Simulink software sinks. Simulation involves compiling a design and checking for any design rule violations. then executing the design to produce the outputs. You can define the inputs of the design using any Simulink tool source blocks, and the output is analyzed either by logging the data to the workspace or by visually viewing the results using a scope, spectrum analyzer, or display block. When simulation is complete, you can review the results by connecting any of the Simulink tool sync blocks to appropriate points in the design. Sometimes it is important to add one or more existing HDL modules to a Vitis Model Composer design. The HDL black box block allows HDL logic components that cannot be realized by any other block in the HDL library block sets, that is, custom logic, to be brought into a design. The black box block behaves like other Vitis Model Composer HDL blocks. It is wired into the design, participates in simulations, and is compiled into hardware. When Vitis Model Composer compiles a black box block, it automatically connects the ports of the black box block to the rest of the design. A black box block can be configured to support either synchronous clock designs or multiple hardware clock designs based on the context and Vitis Model Composer hub settings. Here's the flow for importing HDL using the black box block. When a black box is added to the model, a wizard is automatically launched for identifying the source and HDL code and related source files. It is important that the top level of the custom HDL follows strict port guidelines in order to properly interface with the Simulink environment. If it doesn't, then create an HDL wrapper for the top level HDL that satisfies the black box requirements. Use the help option from the black box block to determine the required interface. Add the HDL, netlist, and memory initialization files required by the HDL for simulation and implementation to the black box configuration M function. Then, co-simulate the black box using the Vivado Simulator or Questa simulation software. The Simulink software does not have the capability to perform HDL simulation. Hence, Vitis Model Composer provides an interface to the Simulink environment and HDL co-simulator. During HDL co-simulation, the black box portion of the design is simulated by an HDL simulator. Two simulators are supported, the Vivado Simulator and the Questa simulation software, which is an external co-simulator. Vitis Model Composer simulates black boxes by automatically launching an HDL simulator, generating additional HDL as needed, analogous to an HDL test bench, compiling the HDL, scheduling simulation events, handling the exchange of data between the Simulink tool and the HDL simulator. This is called HDL co-simulation. Vitis Model Composer provides accelerated simulation through hardware co-simulation, which makes it possible to incorporate a design running into a device directly into a Simulink simulation. Hardware co-simulation allows all or a portion of the Vitis Model Composer design that had been simulating in the Simulink environment as sequential software to be executed in parallel on the device. This can speed up simulation dramatically. The tool will automatically create a hardware simulation hub for a design captured in the Vitis Model Composer HDL block set that will run on supported hardware platforms. This hardware will co-simulate with the rest of the Simulink system to provide up to a 1000x simulation performance increase. The main advantage of this feature is ease of use. You can perform hardware verification without knowing HDL languages, how to run the hardware verification tools, details about the device architecture, board APIs, and device driver details. Now let's look at the flow for creating a homogeneous HLS design. Here we'll go over creating a design using HLS blocks from the AMD toolbox and then simulating the design using the x86 simulator. Let's look at the top-level elements of a Vitis Model Composer design using HLS blocks. In subsequent slides, we'll go into more detail. As shown in the figure here, a Vitis Model Composer design with HLS blocks includes the following elements. An input signal from Simulink software blocks that determines the inputs and provides the source signals, These blocks are used in the simulation of the design, but do not affect the output generated by Vitis Model Composer. The Vitis Model Composer hub block that controls the throughput of the design and output generation, and the output signals or sinks that process the output in the Simulink environment. Again, these blocks are used during Simulink simulation, but do not affect the output generated by Vitis Model Composer. A top-level subsystem block that encapsulates the algorithm defined by the Vitis Model Composer model. This subsystem module can contain blocks from the HLS library to define the algorithm, custom imported functions, and an interface spec block that defines the hardware interfaces. Let's look at how you can create a Vitis Model Composer design using HLS blocks. You can create a new model by adding blocks from the library browser to the Simulink editor. You can then connect these blocks with signal lines to establish the relationships among the blocks. The Simulink editor manages the connections with smart guides and smart signal routing to control the appearance of your model as you build it. You can add hierarchy to the model by encapsulating a group of blocks and signals as a subsystem within a single block. Vitis Model Composer provides a set of predefined blocks that you can combine to create a detailed model of your application. Vitis Model Composer lets you import C or C++ code to create new blocks that can be added to a library for use in models alongside other HLS library blocks. This feature lets you build custom block libraries for use in Vitis Model Composer. The library import feature is the MATLAB tool function XMC import function, which lets you specify the required source files and automatically creates an associated block that can be added into a model in the Simulink environment. Vitis Model Composer does have specific requirements for the code to be properly recognized and processed. The function source can be defined in either a header file or in a C++ source file, but if the function is defined in a source file, then the header file must contain the function signature. You can import functions containing function arguments that are real or complex types of scalars, vectors, or matrices, as well as using all the data types supported by the Vitis Model Composer HLS library, including fixed-point data types. You can change the source code underlying the library block without the need to re-import the block or recreate the library. However, if you change the function signature or the parameters to the function, then you will need to rerun the XMC import function command. The XMC import function command uses the following syntax. Libname is a string that specifies the name of the Vitis Model Composer HLS library that the new block is added to. The library can be new and will be created or can be an existing library. Func names specifies a list, a cell array, of one or more function names defined in the source or header files to import as a Vitis Model Composer block. An empty set imports all functions defined in the specified header file, HDR file. For functions including namespaces, a full namespace prefix needs to be given. For example, to import the function signF in HLS Math, the full function name HLS::signF needs to be specified. HDR file is a string that specifies a header file, .h, that contains the function declarations or definitions. This should be the full path to the header file if it does not reside inside the current working directory. The function signature must be defined in the header file, and any Vitis Model Composer XMC pragmas must be specified as part of the function signature in the header file. Source files specifies a list of one or more source files to search for the function definitions. When used in a model, the header and source files, together with the main header file of the model, header file, will be compiled into the shared library for simulation and copied into the target directory, specified for output generation in the Vitis Model Composer hub block. SRC-H paths specifies a list of one or more search paths for header and source files. An empty set indicates no search path, in which case the code is looked for in the current folder of the MATLAB tool. As an example, the following simple.h header file defines a simple add function with two double precision floating point inputs and a pointer output. The function simply adds the two inputs and returns the sum as the output. To import the simple add function as a block in a Vitis Model Composer HLS library, you can enter the command shown here in the MATLAB tool command prompt, where simple_lib is the name of the Vitis Model Composer HLS library to add the block to. Simple_add is the function name to import. Simple.h is the header file to look in. No C source files or search paths are specified. In this case, the function definition must be found in the specified header file, and only the MATLAB tool current folder will be searched for the specified files. When XMC import function completes, the simple_lib library model will open with the simple add block created as shown here. After the block symbol has been created, you can double-click the symbol to see the parameters of the imported block. You can quickly review the parameters shown in the block parameters dialog box to ensure that the function ports have been properly defined. While it is common to write functions that accept only a predetermined data type, such as int32, in some cases you may want to create a block that accepts inputs of different sizes, supports different data types, or accepts signals with different fixed point lengths and fractional lengths. To do this, you can use a function template that lets you create a block that accepts a variable signal size, data type, or data dimensions. Using function templates in your code lets you create a Vitis Model Composer block that supports different applications, increasing the reusability of your block library. You can define blocks using function templates as shown in the following example. The example uses the template parameters rows and columns. The actual dimensions of the input and output arrays, in1 rows columns for instance, are determined at simulation time by the dimensions of the input signals to the block. Rows and cols are template parameters used to define the dimensions of the function arguments and are used in the body of the I less than rows function. The command shown here imports the function into Vitis Model Composer. Simulation involves compiling a design and checking for any design rule violations, then executing the design to produce the outputs. The HLS design Simulink model defines what data to input at the start of simulation and defines what data to capture during simulation. After the simulation is completed, you can analyze any log data with MATLAB scripts and visualization tools like the Simulation Data Inspector within the MathWorks environment. Now let's look at creating and simulating an AI engine design. Let's now look at creating a homogeneous AI engine design. We'll go over creating a design using AI engine blocks from the AMD toolbox and then simulating the design using the AIE simulator. The Vitis DSP library is a library of commonly used DSP functions optimized for AI engines. To facilitate the use of these functions in a design, Vitis Model Composer provides different DSP lib functions as blocks in the AMD toolbox AI engine DSP library. Vitis Model Composer provides a copy of DSP lib functions that can be used as is. This is synchronized with the DSP functions available in the Vitis library's GitHub. Optionally, you can download DSP lib functions from the online GitHub repository and use the MATLAB tool command xmc library path to set the path to the DSP library functions. AI engine kernels are functions that form the fundamental building blocks of the data flow graph. Model Composer supports generating the AI engine data flow graph by importing the AI engine kernel or subgraph from the AI engine library that is available under AMD Toolbox in the Simulink library browser set. Creating an AI engine design includes two steps: preparing the kernels and importing the AI engine code as a block. Kernels are declared as C++ functions, then return void and can use special data types for arguments. Each kernel should be defined in its own source file. Kernel source files should include all relevant header files to allow for independent compilation. An AI engine kernel can either consume or produce blocks of data, or it can access and produce data streams in a sample-by-sample fashion. The data access APIs for these cases are described as buffer-based access and stream-based access, respectively. Let's look at buffer-based access. From the kernel perspective, incoming blocks of data are called an input buffer, which is defined by the type of data contained within that buffer, and outgoing blocks of data are called an output buffer. By default, the synchronization required to wait for an input buffer of data or to provide an empty output buffer is performed before entering the kernel. There is no synchronization required within the kernel to read or write the individual elements of data. In other words, the kernel will not execute unless there is a full buffer available. The example here shows the declaration of an input buffer carrying complex integers where the real and imaginary parts are both 16 bits wide, and an output buffer carrying 32-bit integers. It is also possible to have overlap from one block of input to the next. This, in general, is required for certain algorithms such as filters. This overlap is referred to as buffer margin. For stream-based access, kernels can access data streams in a sample-by-sample fashion using data access APIs. With the stream-based access model, kernels received an input stream or an output stream of type data as an argument. Each access to these streams is synchronized. There is also a direct stream communication channel between one AI engine and the physically adjacent AI engine, called a cascade. The example here shows a declaration of input and output streams of type CN16. To import the AI engine code as a block, Vitis Model Composer allows you to import either the AI engine kernels from the AI engine library or a user-defined AI engine graph. Vitis Model Composer provides two AI engine library blocks to import kernel functions of different types: the AI engine kernel block, which is non-class based, and the AIE class kernel block, which is class-based. In addition to non-class-based and class-based kernels, Vitis Model Composer also supports the importing of kernels declared in a namespace. When importing the AI engine kernels, Vitis Model Composer will create a block with an interface that has input and output ports equivalent to the arguments of the AI engine kernel functions. The tool also provides the flexibility to configure the kernel parameters using the block parameters dialog box. Now let's look at non-class-based kernels. To import a non-class-based AI engine kernel as a block into Model Composer, you will need to use an AIE kernel block from the AI engine library. Double-clicking the block symbol displays the parameters of the AI engine kernel block as shown. You will need to update the block mask parameters in order to import the kernel function as a block. Model Composer supports importing both buffer-based and stream-based kernels. The tool also supports cascade stream connections between two AI engine processors. Once done, click the Import button in the Block Parameters dialog box, and the tool parses the function signature in the header file and updates the AI engine kernel block GUI interface. After the AIE kernel block is added to the Simulink editor, and after the kernel parameters are added, the block is updated with two input ports and one output port with a block name that matches the imported kernel function. After a successful import, the Function tab displays automatically, providing user-editable configuration parameters. Model Composer also supports importing AI engine kernels with runtime parameters and function templates. The function templates are generic functions that can be used to pass different data types as parameters with an option for template specialization. Now let's look at class-based kernels. Vitis Model Composer supports importing the C++ kernel class to have constructor parameters for specifying parameter values. You will need to use an AIE class kernel block from the AI engine library to do this. Double-clicking the block symbol displays the parameters of the AI engine class kernel block. The AI engine class kernel block supports all the kernel functions that a normal AI engine kernel block can support, and the same block parameters irrespective of whether the kernel member function is buffer-based or stream-based. Vitis Model Composer supports kernel classes with default constructors and class kernels with parameterized constructors. Default constructors do not take any arguments and have no parameters. However, it is possible to pass arguments to the constructors using the parameterized constructors. Vitis Model Composer supports importing the kernels with class templates using the AIE class kernel block using template specialization. A graph is a connection of different compute kernel functions. Unlike when importing kernels, where a kernel function is imported as a block into Model Composer, in this case, graph code is imported as a block. To import the graph as a block into Vitis Model Composer, you will need to select the AIE graph block from the AI engine library. Vitis Model Composer allows connection between the AIE graph block and the AIE kernel block so that the whole design can be simulated in the Simulink environment. The AIE graph block supports importing the AI Engine graph into Model Composer by using the .h header file. To import the graph using the header file, double-click the AIE graph block and specify the graph header file, class, search paths, and preprocessor options. When the GUI parameters are updated, click Import. The tool generates the graph database, and after successful import, the AI Engine graph block gets updated with input and output ports. Parameters such as the graph port name and data type are automatically updated from the graph code. Note that importing a graph class that has PLIO attributes specified is not allowed. If this is attempted, Vitis Model Composer will generate an error message. For the AI Engine flow in Vitis Model Composer, after a high-level graphical design is created using the blocks available in the Vitis Model Composer AI Engine library, the design should be simulated interactively in the Simulink environment. This process ensures the functional correctness of the design using the native Simulink functional simulator and displays the results on scopes and graphical displays. Vitis Model Composer provides two MATLAB environment utilities, XMC Vitis Read and XMC Vitis Write, to directly read, write data from or to the files that are formatted for the AI Engine simulator and/or the x86 simulator. Clicking the Simulate Model icon in the Simulink Simulation toolbar compiles all the kernels and graphs in the design. You can monitor the status from the progress window, which displays after simulation begins. When simulation is complete, you can review the results by connecting any of the Simulink tool sync blocks to appropriate points in the design. Now let's look at creating a heterogeneous design, which includes AI Engine and PL components. Let's go over creating a heterogeneous design using AI Engine plus HDL and/or HLS blocks targeting both the AI Engine and programmable logic resources in AMD Versal devices. Here is a typical heterogeneous design flow. It starts with the AI Engine kernels and data flow graphs being imported into Vitis Model Composer as blocks. The behavior of the kernels and graphs can be controlled by configuring the block GUI parameters. The programmable logic kernels can be written using RTL or HLS C++ functions. The connection between the AI Engine and the PL blocks is routed through dedicated connector blocks. Vitis Model Composer supports targeting both first-generation AIE and AIE ML devices. Vitis Model Composer takes advantage of the versatility of the Versal Adaptive SoC's heterogeneous system by interconnecting the Versal device's various domains, including the AI Engine, HDL, and HLS kernels. This diagram shows connector blocks are used to connect the different domains. Let's look at the types of connecting blocks in a heterogeneous design. An AI Engine kernel written using specialized intrinsics and imported into Vitis Model Composer can be used as part of a larger Versal Adaptive SoC system design. In addition to the kernels operating on the AI engines, you can also specify kernels to run on the programmable logic region of the device. The PL kernels can be written using RTL or HLS C++ functions. The connection between the AI engine and the PL block is routed through a physical channel interface tile, and conceptually, the data width of the connection is 32, 64, or 128 bits. Vitis Model Composer allows connecting an AI Engine kernel to an HLS PL kernel only if the data types and complexities of these ports match. If the data types or complexities of the ports of the AI Engine kernel and the port of the PL kernel do not match, interface blocks should be used to reconcile the discrepancies. In the next few slides, we'll go over interconnecting HDL blocks or HLS C++ functions with AI Engine kernels. In order to properly manage the sampling times across two domains and simulate a heterogeneous system with both PL, modeled with HL blocks, and AI engines, Vitis Model Composer provides interface blocks in the Utilities library to connect from AI Engine to HDL blocks and vice versa. The AIE to HDL block connects AI Engine to HDL blocks using an AXI4 Streamlike interface. The HDL to AIE block connects HDL to AI Engine blocks using an AXI4 Streamlike interface. You can find these blocks in the AMD Toolbox Utilities Connectors library. The figure here shows the connections between AIE to HDL and HDL to AIE blocks. You can see that there are T-valid and T-ready ports as depicted in the figure. The gateway from the AI engine to the HDL domain can accept a vector input, but it generates a scalar output, meaning that in the Simulink environment, the HDL domain will run at a different rate than the AI engine domain. Let's now look at how to set the block parameters of the AI engine to HDL block. The AIE to HDL block connects the output of an AI engine block or subsystem with the input of an HDL block or subsystem. This block accepts variable size signals from AI engine blocks along with the T-ready signal, which indicates whether the HDL domain can accept the data. The input data type to this block is inherited from the input signal. Note that if the HDL domain T-ready signal stays low for a long time, eventually the internal buffers in the AIE to HDL block will overflow and the simulation stops. The bit width of the T data output of the AIE to HDL signal is limited to 32, 64, or 128 according to hardware functionality. The HDL to AIE block connects the output of an HDL block or subsystem with the input of an AI engine block or subsystem. This block accepts T data, which is the primary input for the data, and the T valid signal, which indicates that the producer has valid data. The bit width of the T data output is limited to 32, 64, or 128, according to hardware functionality. Output from the HDL to AIE block is a variable size data signal to the AI engine block along with the T-ready signal, which indicates that the block can accept a transfer. A transfer takes place when both T-valid and T-ready are asserted. Connections between an output port of an AI engine kernel and an input port of an HLS kernel use an AIE to HLS kernel block. Connections between an output port of an HLS kernel and an input port of an AI engine kernel use an HLS kernel to AI engine block. These blocks reformat the data to match the data type of the sync port. During this process, no data or information is lost. The blocks are simply adjusting the data type and the number of samples. For example, an interface block can reformat a signal carrying 64 int8 values to a signal carrying 16 int32 values. Use of these blocks is not mandatory if the data types between the HLS kernel block and the AI engine block match. Interface blocks are available from the AMD Toolbox Utilities Connectors library. The AIE to HLS kernel block reformats a signal driven by an AI engine kernel block or an AI engine subsystem. For example, if the AI engine kernel output port is of type CN16 and the HLS kernel is of type AP-Access64, for the resulting signal to match the data type and complexity required by the input of the HLS kernel block, you would use an AIE to HLS kernel block with the parameter output type set to AP-Access64. This reads CN16 samples from its input and then packs pairs of subsequent CN16 samples into AP-Access64 samples to its output. Double-click the block symbol in the tool environment to see the parameters of the AIE to HLS kernel block. Output type values are shown here. The output port is a variable size signal whose maximum size is specified by the output size parameter. The default output size is 1. Now let's look at HLS kernels to AIE. The HLS kernel to AIE block reformats a signal driven by a port of an HLS kernel block so that the resulting signal matches the data type and complexity required by an AI engine kernel or an input of an AI engine graph block. For example, if the data type of the port of the HLS kernel block is AXI-U128 and the data type of the port of the AI engine is UN32, the HLS kernel to AIE block reformats the input samples by unpacking each AXI-U128 sample into 4 unsigned int32 samples. The output port of this block is a variable size signal. Double-click the block symbol in the tool environment to see the parameters of the HLS kernel to AIE block. Possible output type values are shown here. The port is a variable size signal whose maximum size is specified by the output size parameter. The default output size is 1. To summarize this technical module, AMD Vitis Model Composer is a model-based design tool that enables rapid design exploration within the MATLAB MathWorks Simulink environment. Vitis Model Composer provides features such as analysis, debugging, and visualization, co-simulation of the AI engines and programmable logic, code generation, and validation of the design and hardware. Creating a Vitis Model Composer design consists of 3 steps: adding blocks to a model, connecting the model, and then creating a top-level subsystem module. Finally, you can run Simulink simulation for functional verification of the design. And this concludes our technical module. Thank you for watching.